Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest, maximum sum of almost unique subarray. The problem is bit easier than the usual third problem of biweekly contest, but anyways, we'll look at this problem and then we'll look at one harder version of this particular problem. If you are here just to watch the harder version, you can skip to that part. All the timestamps will be there in the description down below, and at the very end we will look at one smaller variation of the harder version as well, so you can watch that if you are interested. So with that, let's get started. The problem states that you are given a integer array nums and two positive integers m and k. You have to return the maximum sum of all almost unique subarray of length k. If no such subarray exists, you have to return 0. A subarray is called almost unique if it contains at least m pairwise distinct element, right? So let's take an example. Let's say nums is 267317, m is 3 and k is 4. So it means a subarray is called almost unique if it contains at least 3 distinct element, and we need to find the maximum sum of all almost unique subarray of size 4, right? So these are the three subarrays of size 4, and all these three subarrays are almost unique. Why? If you look at the first subarray, it contains 4 distinct elements, 2, 3, 6 and 7. Similarly, if you look at the second subarray, it also contains 4 distinct elements, which is greater than 3. And if you look at the last subarray, it contains 3 distinct elements, which is again greater than equals to 3. So all of these 3 subarray are almost unique. We just have to figure out which one has the maximum sum, and if you just sum them all up, you can find out that this subarray 2673 has the maximum sum of 18, and hence 18 is the answer, right? So hope the problem statement is clear. Now how to solve this? So let's say the value of m is 3 and the value of k is 4. It means we have to figure out the maximum sum of all the subarray of size 4 which are almost unique, or in other words, which contain at least 3 distinct elements, right? So if we see k is 4 here, so if you try out all the subarrays of size 4, this is the first subarray of size 4, right? Now for this subarray to be considered, this subarray should be almost unique. In other words, this subarray should contain at least 3 distinct elements, right? So we need to find out how many distinct elements are there in this subarray. If we are able to figure out this, then we can simply say whether this subarray is good or not. If it is good, we will just find its sum and consider it while finding out the final result, right? So this is first subarray, and then we can try out the same thing for the second subarray, right? And we can try out the same thing for the third subarray, and so on and so forth. So we will try this out for all the subarray. Whichever gives us the maximum sum, whichever is valid and gives us the maximum sum, will be the answer, right? So that's the very brute force approach. We are just simulating whatever we are given in the problem statement. Now how to find out the number of distinct element in this range L to R? So to find out the number of distinct element, what you can do, you can simply iterate over the array and see if the element already has occurred or not, right? That's a very simple way to find out the number of distinct elements. So let's say you maintain a map, right? And you will just simply say if you have already seen an element or not. So in this case, 1 is the first element. You just increase the frequency of 1. So you have seen 1 time. Now next is 3. So you increase the frequency of 3. So you have till now you have 2 distinct elements. Why? Because you increased the frequency of something which doesn't exist before. Previously the frequency of 1 was 0, previously the frequency of 3 was 0, and you increased them to 1. It means you just had one element which you haven't seen before, and hence you just had two distinct element in your current subarray. Now you got at index 2, which is the value of which is 1. Now you got at index the value 1. You see you already had the frequency of 1 here. It means 1 was already there. So with this new addition of element, number of unique element doesn't increase, right? In the same fashion, you get on to the index 3, you again saw 1, so you again increment the frequency of 1, but again because the frequency of 1 was not 0, it means you already have seen 1 before, and hence the number of distinct elements stays as 2. So once you go over all the elements from L to R, you now see, okay, you have two distinct element. You can now answer whether this subarray is good or not. So in this particular case, the subarray is not good because you want at least 3 distinct element. So the subarray is not good, and hence the current subarray you will not include in while calculating the result, right? Now you want to calculate the same thing for the next subarray, right? Now you can do the same process all over the again. Basically you can say, okay, I will reset the frequency of everything. Now I will try out the same thing starting from this particular L. But if you do this, the complexity of your solution would become n into k, right? Because you are iterating over n subarrays and each subarray is of size k, right? But you can simply reduce or reuse most of the work. So you can you saw that you just increase the frequency of everything from this L to this R, right? Now if you want to calculate something from this L to this R, whatever you have done with these elements, they should stay as it is, right? You only have to remove the contribution of this element and add back the contribution of this element, right? That's the only thing you need to do. So what we will do, instead of iterating over all the elements again, we will simply remove the contribution of the previous element and add back the contribution of new element which got introduced when we incremented R, right? So if you remember, previously the frequency of 1 was 3, right, and the frequency of 3 was 1 with this particular subarray, right? Now we want to remove the frequency, we want to remove the contribution of 0. How you will do that? Simply decrease the frequency of 1. So if you decrease the frequency of 1, this will become 2, right? Now if you decrease the frequency, does the distinct element count decrease? The answer here is no, because the distinct element previously was 2 and you just remove 1. There were 3 ones, you removed 1 of them. So number of distinct elements still stays the same. With this 1 removal, the number of distinct element doesn't decrease because this was not the unique element. We still have other ones, so we still have 2 distinct elements with us, right? So that's where the number of distinct element count still stays 2, and we now have to add back the contribution of this particular element. So we just increment the frequency of 3 to 2. Now again with this increment, the number of distinct element doesn't increase because we already had 1 3, we just had 1 more 3, so number of distinct elements still stays the same, right? Now we saw number of distinct element is 2, but we want at least 3. So even this subarray, this particular subarray is also not good. We will try the same for the next one. Let's try one last time. Again we will remove the contribution of this particular element and add back the contribution of this element, right? So if you remove the contribution of this element, the frequency of 3 will now decrease to 1, but with this decrease, number of distinct element will not decrease. Why? Because you had 2 3s and you just removed 1 3. So you still have 1 3, and hence the number of distinct elements still stays the same. In the same fashion, you incremented for the frequency of 4 to 1. This you added this element. Now if you added 1 4, you just saw that previously there were no 4, but you just added 1 more 4. So in this case, you added a new element, and hence number of distinct element will also be increased. Now you can see number of distinct element is 3, and the value of m is also 3. It means this particular subarray is a valid subarray, or is almost equal subarray, and hence this is a valid subarray. So you will just take the sum 4 plus 3 plus 1 plus 1, which is 9, and you will just take the maximum of this with your current result. So current result was 0, so maximum of 0 comma 9 is still 9. Now you will try with similarly you will try with other elements as well. So you will again increment L, you will again increment R. Again you will do the same thing, remove the frequency of 1, the frequency of the previous L, and add back the frequency of new R. You will keep on doing this unless you have explored all the subarrays of size k, and finally you will have the result with you. So what is the overall time complexity? So in each iteration you are incrementing L by 1 and you are incrementing R by 1. Now with this increment you are removing the contribution of the previous element and adding back the contribution of a new element. So in total, in one iteration you are doing 2 operations, and you will be doing order n iteration in worst case, and hence you will be doing order 2n operation. So overall time complexity of this entire algorithm is order n, with order n space, because you are maintaining this frequency map with you, right? So you can implement this entire algorithm by yourself. I am not showing you the pseudocode because this is exactly similar to the dry run simulation that we just saw. So next we look at the code, and then we look at one harder follow-up. So the code is straightforward. As we discussed, we will just iterate over all the subarrays of size k. Initially our L will be here and R will be at k minus 1, right? So we also need to maintain this frequency array, number of distinct element, and the sum of the current subarray as well, because this is something you need to have so that you can take the maximum of this sum if this particular subarray is valid, right? So we take initialized sum with 0, number of distinct element with 0, and we also maintain a frequency map. Now we are adding the contribution of elements one by one. So whenever we see a new element, we add the contribution of new element. Basically we incremented the frequency. We checked if the frequency is 1. It means previously it was 0, now it is 1. It means we just saw one unique element with the addition of this new element. So we just increased the number of distinct element that we have, and similarly we increased our sum because we want to maintain the value of sum as well. Now we will keep on doing this until we hit the k minus 1 for the first array. So if you look at this, when L was this, R should be here, right? So what I am doing is we will simply add the contribution of these 3 elements beforehand without worrying about whether the subarray is valid or not, because you only care about the subarray of size 4. So any subarray of less than size 4 doesn't matter. So we will keep on doing this until we have finished k minus 1 elements. Now as soon as we hit the kth element, that's the point we will see if the number of distinct element that we have, if this value is greater than equals to m or not. If it is greater than equals to, then the current subarray is valid. We will just take the sum and take its maximum with the result. So if distinct is greater than equals to m, we will just take the maximum of the sum with the current result, because the current subarray is valid. Now if this is not the case, we will simply decrease the frequency of the previous array, because if you think about it, the next subarray that will be encountered is this one, right? So we need to now remove the frequency of this element. So what will be the index of this element? Index of this element would be r minus k plus 1. So index of this element would be j minus k plus 1, and we will simply remove the frequency. If the frequency becomes 0, it means we removed an element such that there is no more occurrences of that element, and hence we just now lost one unique element, and we decrement the unique number of unique elements, and finally we reduce the sum as well because that element is now gone. So we'll keep on doing this until we explode all the subarray of size k, and finally the value result will contain the maximum sum of all the almost unique subarrays. That's what we want. So hope this entire solution makes sense. If you have any doubts in this particular solution, feel free to post them in the comment section below. I would be happy to answer. The next problem is slightly harder. It says you have to almost unique subarray is something which has exactly m, not at least, which has exactly m distinct elements, and we haven't given the value of k. It means we can take any subarray which has exactly m distinct element. So from all the subarrays which have exactly m distinct elements, we have to return the one with the maximum sum, right? So let's say this is the value of we will try out all possible subarray. So we'll start with subarray which starts at index 0, right? Now for this subarray there will be an index up till which the value of distinct element will be equals to m. So if you look at this, for this L, this is the first element where the value is exactly equals to m, right? Now at this element you will simply figure out what is the sum of this particular range and take its maximum with the result. So for all L you have to find out what is the valid R. In other words, for all L you have to find out the point R such that in between L and R there are exactly m number of distinct elements, right? So how will you find that? I would encourage you to pause the video right away and try to solve this problem by yourself. So hope you have thought about it. The actual the brute force solution would be you will try out R one by one. So you will start your R with L itself. Again you have to figure out the number of distinct elements. So you will keep on maintaining your frequency map. You saw 1, so you incremented the frequency of 1, and you incremented your number of distinct element as well because you just incremented the frequency of an element which was 0, right? So you found one unique element. Now similarly you incremented L because this is not equals to m, right? You want number of distinct elements to be equals to m, so you incremented R. You found 3, you incremented the frequency of 3. With this increment the number of distinct element now become 2 because you just incremented the frequency of an element which was not there previously. Similarly you incremented R, you incremented the frequency of 1, but this time number of unique element will not increment, right? You incremented R, number of 1 increased, but again number of distinct element doesn't increase. You incremented R again, number of 3 is increased, but number of distinct element will not increase because 3 was already there. And finally you incremented R, 4 increased, and with this the number of distinct element will also increase, and hence at this point you have the first R where number of distinct element is equals to 3, and hence this particular range is a valid range, and you will just take the sum and you will do the same for all the else and return the answer. So what is the time complexity of this brute force approach? Obviously order n square, because for each L you are iterating over every possible R, or you are iterating over R incrementally until you hit the valid value of R. So in worst case it can go up to order n square. Now how to optimize this? So there are two solutions that should come to your mind on optimizing this. First thing, you are saying that okay, you are searching for R in a linear fashion, and that's where this second n is coming from. So you can say okay, instead of trying out this linear search for R, is it possible for me to try out binary search, and in that case I will be able to reduce this one extra n and replace it with log n, because binary search will take log n time. And once we get the r, I can simply maintain a prefix sum, something like this, and I can take the find out the sum of this range easily with the help of this prefix sum, right? So that can be one approach. The second approach could be, okay, I will not apply binary search. Instead, let's see if R satisfies strictly increasing property. So we have solved multiple problems of this kind before. Basically, if R, the main issue with this entire n square algorithm is, for this L we hit this R, but for the next L we need to reset R to this and then again search for R one by one, right? So if we can somehow save this reset of R, then also we can optimize and remove the extra n from the time complexity. So that's the idea. Let's look at both the ideas one by one, binary search as well as this one. So let's start with the second one in this particular scenario. So for this L, you found that this R is a valid R, right? Now for this L, do you need to reset the R, or basically for this L, what could be the probable candidates for R? Does R can be any of these indexes? I would encourage you to pause and try to think at least for 5 minutes if what is the answer for this particular question. Now for this L, this R will never be this any of these R will never be valid. Why? Because you know that number of distinct element between this position and this position was 3, right? Now you just removed one element. Removing an element will either decrease the number of distinct element or keep it same, right? We just saw, we have seen this in the previous solution. So if we remove the contribution of 1, let's say, so it will remove the frequency of 1 to 2. So either the number of distinct element will stay the same, and or let's say in this was 4, just an example. In this case you will remove the frequency of this 4 to 0. In this case number of distinct element will be reduced to 2. So either it will be reduced or it will remain the same. And if it is reduced, you know that you will increment the R to find out your valid R. If it stays the same, then this is the first valid R that you have, right? So in both the scenarios, none of these R which was already skipped can be a probable candidate, and hence what you can say is, okay, I will not reset the R, I will keep the R as it is, and I will just subtract the contribution of whatever is already done. So I'm already finished with this particular L, so I will just remove the contribution of this particular L, reset my or adjust my number of distinct element based on this. So in this case number of distinct element will not be increased or decreased because the value is still the same. Now I will simply see if number of distinct element is less than equals to m or not. If it is not, I will keep on incrementing R. If it is, I will, this is the valid R, right? So this way you are not resetting your R, you are simply either incrementing your R or keeping your R the same. So your R is strictly increasing. It started from here, it will go all the way to here just once. So every index is visited exactly once, and in the same fashion L is also visiting every index exactly once. So overall time complexity is just order n instead of order n square, right? And just to reiterate this part, we have to take the sum across this L and R, so you can just simply maintain a prefix sum to get this sum efficiently, right? Now there is just one small edge case. I would encourage you to pause and think about the edge case. The edge case would be, what about there are more 4s, right? So How will you solve that? Hope you have thought about it. Let's just take an example. Let's say there is one more 4. So in this case, the value of this L would not be this R, rather this R, right? So you want R to be maximum possible. Otherwise, the number of otherwise your sum will not be maximum possible. So if you take this R for this L, whatever sum you will get will be less than whatever sum you will get if you increment your R, right? So you want to push your R as much as you can, right? So you will not stop your search as soon as you hit the value of M. Instead, you will keep on moving your pointer until it remains M. So that's one small difference, right? You will not stop until you hit M. Instead, you will keep on moving the pointer until it remains M. And with that, you will be taking care of this particular scenario, edge scenario as well. So hope this solution makes sense. Now let's look at the second solution, which was using binary search. So basically what we have to find out is what is the valid value of R for this particular L. We instead of doing linear search, we want to do binary search. Now if we want to do binary search, first of all, can we do binary search? So if you are new, there is a complete binary search video from scratch. I will link that. So just to reiterate, binary search, you will divide your sample space in half. If you are deterministically able to say whether to search in the left or to search in the right, if you are able to say this deterministically, then you can apply binary search. Otherwise you can't, right? So in this particular scenario, if let's say we pick this particular index, so this is my current index I, right? Now if number of distinct element between L and I is less than M, does it make sense to search in any of the value in between L and I? The answer is no, because if number of distinct element between L and I is still less than M, any of these elements, number of distinct element between L and those element will still be less than M. So it doesn't make sense to search in the left part, so you can skip the left part and search only in the right part. In the same fashion, if the number of distinct element between L and I comes out to be greater than M or greater than equals to M, then we will search. So if it is greater than M, then we will only search in the left half, because if it is already greater than M, if we move forward, it will be more greater, not lesser, and we want exactly equals to M. So that's where we are able to say deterministically whether to search in the left or right half, and hence you can apply binary search. Now the only question is how to find out the number of distinct element between L and I efficiently, because the approach that we saw previously was iterating over the entire element between L and R. So we don't want to do that, so we have to figure out an algorithm that can give us the number of distinct element between L and I using in log n time using some technique. So I'm already using segment tree in this channel. I would encourage you to pause the video and try to at least think about that problem, think about that solution. So the solution is straightforward. There is a small trick that you need to apply. What exactly is distinct element? So let's say you want to find out the number of distinct elements between this L and this R. Now distinct element definition is, if an element is there, the previous occurrence of this element should not be within this range. So in this case 1 will not be counted because the previous occurrence of 1 is still in this range, but this 1 will be counted. Why? Because the previous occurrence of this 1 is not in the current range L to R. Similarly, this 3 will be counted. Why? Because previous occurrences of this 3 is not in the range L to R. And similarly, this 4 will be counted because previous occurrence of 4 is not in this range, and the same with 7 as well. So if you see, we are not counting something if it occurs already in this range, right? So we will take this advantage and prepare another array which will just say what is the previous occurrence of a particular element. So previous occurrence of 1 is nothing, like we can, for whatever there is no previous element, we will just simply replace it with, let's say, -1 or something of that sort. So there is no previous element of 1, so -1, no previous element of 3, -1. For this, the previous element of 1 is index 0, so we put it index 0. And similarly for this particular thing, the previous element is at index 2, so we put index 2, and so on and so forth. Now for any range, whenever we need to find out the number of distinct elements between a range, we will simply figure out the number of element less than equals to L or less than L in this particular range. The count of such element will give us the number of unique elements in this range, right? So would encourage you to rewind the video and watch it again if you didn't understand it. We just need to find out the number of distinct element in a particular number of element less than some x in a range L to R. This is the exact same problem that we have solved a few videos back using merge sort tree, and I will be uploading one more video sooner, sometime this week, and we will be solving the same problem using persistent segment tree as well. So if you have watched the merge sort tree video, I think it is k-query or giveaway, but I think it is k-query. So this is exact same problem, finding out the number of element less than equals to x between the range L and R. So if you have watched that video, you should be able to solve this problem by yourself. If not, I would encourage you to watch the video, which is this. I will link this particular Google Doc, which is bit.ly / segment trees, in the description down below, which has all the videos that we have discussed so far in the segment tree series. So with that, we are able to find out the number of distinct elements between a range in just log n time using segment tree, and the overall solution using binary search will now work in n log n square, because for trying out one single I, we require log n time, because we want to find out the number of distinct elements between L and I. So we will be trying out log n number of i's, so the complexity would be log square n for a single L, and we will be trying out all possible L, so complexity would be n log square n, right? So this was just a follow up, so that because we are doing segment tree series, so I thought this might be a good practice problem for you. But as we seen, there is, with just 2-pointer approach, there exists a very nice order and solution for the same problem as well. So with that, I hope you learned something new. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.